All right, I've got two solutions set up here, a solution of sodium fluoride and a solution of magnesium nitrate. Now, both of these are dissolved in solution. Neither of these are solid. And I want to know if I mix these together, that's what this plus means. If I mix these together, will I form a precipitate? So first, we're going to be putting this not only in a molecular equation, that's what this is, but we're also going to do a ionic equation and a net ionic equation. I'll make sure we learn how to do all of these. Okay? So first off, let's write out the ionic equation. Well, since these are aqueous, that means that we're going to be splitting up into the separate ions here. And now I want to know if any of these combinations are going to produce an insoluble compound. And so I'm going to use this chart over here. I'm going to go over to this chart, and I'm going to find my reactants. So I've got, what did I say, sodium fluoride. So I started with sodium fluoride. Here's sodium, down to fluorine. That's the top one. That's going to be soluble, right? And that's what I said, starting with sodium fluoride, which is soluble. Okay? So first I need to check if my sodium combined with my nitrate is going to be soluble or insoluble. Now, why am I checking sodium and nitrate? Well, these are ionic compounds. They're only going to go plus to minus. And I already know that sodium and fluorine, that's going to be soluble, that is going to dissolve. So I need to check sodium and the nitrate. I need to check the ones that I don't already know. So sodium and nitrate together, I can just come over here. I can look sodium and nitrate right there. That's going to be soluble. And so the NaNO3, I could write this up here. I could say NaNO3, and I know it's going to be just like that because it's going to be 1 plus and 1 minus. That's going to be aqueous. That's still going to be an aqueous solution. So then I could write these guys down here, Na plus NO3 minus, okay? Now let's come back over here and let's check magnesium. Magnesium is already bonded to the nitrate, so I don't need to check that. I just need to check if the magnesium and the fluorine together will make a solid. So I come over here and I look. There's my magnesium right there. So my magnesium, I go down to my fluorine, and I see that it is insoluble. And so that means it's going to form a solid compound. And so I can write that in. Magnesium, Mg, and F, and that's going to be F2 because there is 1 minus here. That's going to be solid. Great. And so then I'm going to add that to my ionic equation because MgF2, that's going to be solid. It's not going to be an ion. And so now that I know what's going to be produced as a solid, I can write my net ionic equation. And so that's going to be only the business parts of this. So only the Mg2 plus the F minus making MgF2 solid. And so now I just need to balance this. I have 2 fluorines here, right? I need 2 fluorines. Then up here I've got 2 nitrates on this side. That means I'm going to have 2 over here. And I'm going to have 2 fluorines. And if that's how this is balanced, well then this top one, this molecular equation, that's going to be pretty easy to balance. I'm just going to copy what I've done down here. I just know that I need 2 nitrates on my right side and 2 fluorines on my left side. And now everything's balanced. Perfect. Nice and easy. Let's do another one. All right, I've got another situation set up here. I've got FeBr3. This is iron 3 bromide being mixed with lithium hydroxide. So, Mr. Parentheses there. So first off, I'm going to write out my ionic equation. I'm going to have Fe, that's going to be 3 plus, right? I'm going to have bromine, it's going to be Br minus. I'm going to have lithium, it's going to be 1 plus. I'm going to have hydroxide. And by writing this out, this is going to help me to identify which molecules do I actually need to check. So let's start with the iron. I'm going to check it against the hydroxide. I already know that it's aqueous with the bromine, so I just need to check it against the hydroxide. So take the Fe. I'm going to find Fe up here. It's right here. And I'm going to check it against hydroxide, which is right here. So if I bring that over, I see that it is insoluble. Okay. So I can write that in here. Fe, and it's going to be OH That's going to be solid. And I know it's going to be OH3 because OH only has a -1 and Fe has a +3, back to when we were putting together molecular compounds. And so I can write that in here too. FeOH3. Am I done? No, I still need to check the lithium. So let's make sure that the lithium and the bromine don't make a complex that is also insoluble. So let's find the lithium. It's going to be right here. And the bromine, it's going to be right here together. They are soluble. Okay. And so that means that I've got lithium bromide in aqueous solution. And so let's write that in here too. The lithium stays dissolved, and so does the bromine. So my net ionic equation here is going to be Fe3 plus 3OH minus combining to make FeOH3 solid. Okay, and then we can easily balance this. Great. Put a 3 here, and then we're going to need a... That should be good there. And then up top, I'm going to need 3 hydroxides on my left side, which means I'm going to need 3 bromines on my right side. There we go. Nice and balanced. Now, what's the point of this net ionic equation? I mean, I get writing out the ionic equation. I could use that to identify which ions I need to check for solubility. But the net ionic equation, what's the point? Well, we're not always just going to be dealing with 2 solutions. We could think of something like seawater, which is going to have maybe a dozen different ionic substances dissolved in it. It's a plethora of ionic salts. And so I don't want to have to write out every single salt that could be in there, every single ion. I only want to talk about the ones that I'm doing business with. Okay? So let's do one more. All right, for our last example here, we've got copper sulfate and barium hydroxide. So let's write out our ionic equation. I'm going to have copper, 2 plus sulfate, SO4, 2 minus. And I know this is the copper 2 plus because the sulfate is the 2 minus and there's only one copper there. It has to balance. And then I've got barium 2 plus. I know that is 2 plus because barium's always 2 plus. And then the hydroxide. All right, I've got 2 of those from this. So let's go ahead and look at the barium versus the sulfate. Let's start with that one. So barium versus sulfate. Where is it? Barium, there it is, versus sulfate. Barium versus sulfate, that is insoluble. So barium, BaSO4, that is going to be solid. Okay, let's put that up here. BaSO4, solid. Great. And then let's double check. Let's just make sure the copper and the hydroxide don't form a complex before we move on. Copper 2 plus is going to be right there. And the hydroxide is going to be right there. If I look over, ooh, that is also insoluble. It's going to be insoluble right there. So let's go back. Looks like we have 2 precipitates. All right, so I've got the CuOH2. That's also going to be solid. So both of these are going to be solid. Okay, well, what do I do in this situation? Well, in this situation, both of them are solid, so my ionic equation is going to look the same as my net ionic equation. So these are going to be the same. So I can just put this down here. That would be exactly the same. But what about up top? Do I need to do anything differently? Well, I just need to make sure that this is balanced, and from the looks of it, it is. So that's all I need to do there. I just need to label that both of these are solids. Awesome. So one last note I want to make over here. On this solubility table, I want to look at a few key elements. Let's go with this ammonium ion. Notice it is always soluble. The sodium and the potassium, notice they are also always soluble. And the lithium, the only time that is insoluble is when it's with the phosphate. In addition, notice the nitrate. That is always going to be soluble. Anything combined with nitrate is going to be soluble. Notice the chlorine and this guy. This is acetate. Acetate and chlorine are almost always going to be soluble. There's only one situation where chlorine is insoluble, and there's only one situation where acetate is slightly soluble. So whenever we see these, we should have those identified. Whenever we see them, we can usually guarantee that there's going to be some solubility there. Now, what do we do with these slightly solubles? And what about these blank spaces? Well, this chart is incomplete, and where we're at right now, we're just learning precipitation. And so for our intents and purposes, slightly soluble is going to be the same as being insoluble, because a majority of it is still going to precipitate out as a solid. And these blank spaces, we can usually look them up on Google, but for now, we're just going to treat these like they are insoluble, okay? So anytime you see a blank space, just for simplicity's sake, we're going to call it insoluble.